All right, I'm back. We're on page 312, kind of in the middle, going to do the second problem. So it's a little bit different because this is the graph of f of x, not the graph of f prime. We're told it consists of, from left to right, part of the graph of y equals sine of x plus 2, okay? A quadratic, a linear, and a cubic function. And I guess there's some controversy about this cubic function because the problem also said it's really cubic. Y equals ax cubed plus bx squared plus cx plus d. I don't know what we're going to have to do with that, but something, presumably. All right, so let's see. Identify the critical points of f of x and create a sign chart for f prime. Okay, so critical points. We're going to go piece by piece. I can identify two of them like very clearly right now. And the reason that they are critical points is that the derivative is definitely going to fail to exist at these 2 points. So x equals 2 and x equal, what are these 2? And x equals 4 are definitely going to be critical points. But I can also identify another one. So we're definitely going to have a critical point here because f prime is definitely 0 there. Let's see, what can we do here? So I'm thinking there's going to be a critical point like here and here. But we'd like to find those, right? And so we've memorized this. What's the derivative of sine? So the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine would therefore be negative cosine. The derivative of negative cosine would be positive sine. There's a lot going on. So if y equals, so I'm going to say d dx of sine of x plus 2. So I'm going to take the derivative with respect to x of sine of x plus 2. That's just going to be cosine of x. So if I need cosine of x to equal 0, cosine's never undefined, so we don't have to worry about that. Cosine of x equals 0. So in my mind, the first places that happens are pi over 2 and 3 pi over 2. But that's not good enough because if you look at the graph, we're only interested in -5 to -1. So what I'm going to do is subtract 2 pi from each of these. So therefore, x equals -3 pi over 2, or x equals negative pi over 2. So do these make sense? Negative 1.5-ish? Yeah, these make sense. So these are our first critical points. So critical point, x equals -3 pi over 2, negative pi over 2. All right, so where's our next critical point? X equals -1 is like a very interesting point, but it's not a critical point because it's not even in the domain of the function. So does the derivative exist there? No, it definitely doesn't exist there, but it's not in the domain of the function, so it doesn't make a difference. Okay, the next one I think is that x equals 1. We could do the math for that, but it's like visually very clear that x equals 1 is going to work, so let's not. X equals 2 and x equals 4. X equals 2, x equals 4. So those are critical points because the derivative fails to exist there, but that's okay. Now we have this thing. So we're told that it's a cubic, and like some cubics will give you critical points that are neither maximums nor minimums. It just like showed up too early. So what I'm going to do is I'm going to find the equation of this thing. So how am I going to do that? I know that it goes through, so let me see. I know it goes through 4, 5. I know that it goes through 5, 3. I know that it goes through 6, 2. 1, 2, 3. That had 3 points. I need a 4th point. So let's say it also goes through 7, 1. I'm going to use a calculator to just give me this equation. So I'm going to do a system of equations here. So let's share the calculator. And new problem, I guess. New problem versus new document, like it's up to you. I think new problem is probably more useful in more circumstances because you get to like store what you previously had. So a times x cubed, b times x squared, c times x plus d. All right, so I want to solve a system. Menu 3, 7. I don't know why I didn't just press 7. And then enter. So how many unknowns, how many equations? So I'm going to have 4 equations. My unknowns are A, B, C, and D. Okay, so I know that f of 4 should be 5. F of 5 should be 3. So if you're a random person watching this, we've done this before in my classes, where we would find like the equation of primarily quadratics that were like super weird. We did it in conic sections when we learned those kind of frequently, or in like notes 13-ish. I don't know. Let's see what we get. Oh, well, this is pleasant. So let's say f of x such that this, can I like complete? No, you can't really complete the square on that. Is there anything I could do to like make this nice? I don't really think there is. All right, well, okay, so the question is, does the derivative ever equal 0? So of the answer, let's say. All right, let's see. Let's solve this. Solve. So I want to solve the derivative equals 0 for x. False, never equals 0. Good. No critical points there. So that's good because I did not want to deal with that. I will be back to this though, I think, because I think in maybe the next part I have to write a piecewise function for this thing, which I don't really want to do, but I'm going to do it. All right, so let's go. Let's share this. We're thinking about it, and we're back. Okay, so we found the equation. We found there were no critical points. So let me actually erase this. And now we're supposed to make a sign chart. So we're making a sign chart for f prime, which will tell us what f of x is doing, but we're doing it backwards because we already know what f of x is doing. So really, our sign chart, all right, so -3/2, -3 pi over 2, I should say, negative pi over 2. All right, so -1 is going on our sign chart because things can happen there. They don't in this case, but things could have happened. You could change increasing, decreasing, decreasing, increasing. There's no way to know unless you unless you have all the information that we have, which we do. And then 4. Okay, so this is for f prime, so we should label it as such. And you can look and see, right? So increasing versus decreasing. Increasing here, increasing here, and here, increasing here, and that's it, right? So I'm going to put pluses on those, and I'm going to put minuses everywhere else. So it's increasing, and then decreasing, and then increasing, also increasing, then decreasing, increasing, and then decreasing. And I got that just by looking at f of x, right? If I know f of x is decreasing, I know f double prime is negative. I know f of x is increasing. I know f double prime is positive. So it's really not that bad. Piecewise function. There's like 0 chance I'm going to squeeze this in here. Well, maybe. I'm going to do it over here where it's like at least a little bigger. Okay, f of x is. We're actually just told that it's sine of x plus 2. So let's start with that. Sine of x plus 2. And that's going to be when we're between -5 and -1. -5, is -5 an open circle, a closed circle? I feel like we could close circle it. So let's include it. -1 is definitely an open circle because it doesn't exist there. All right, I need to find the equation of this equation, and there's a lot of ways you can do this. I'm going to say it's y equals, so the vertex is 4. And then if I move over 1, I go down 1/2. If I move over 2, I go down 4. So it's going to be minus 1/2 x minus 1 squared. So 4 minus 1/2 x minus 1 squared. 4 minus 1/2 x minus 1 squared. And that's between -1 also not inclusive. And then we could include it at 2. You could also include 2 for the line segment. It doesn't make a difference. So in general, what I did here was I kind of used the form y equals k plus a x minus h squared. I filled in k and h, right? The vertex is hk. And then I know you need to know one point. So you could just use the point -1, 2, for example, and solve for a. That's how I would do that if I wasn't just kind of like trying to intuitively go through it and get it. But I thought it'd be a little faster to just like do it, you know? All right, let's see. The slope here for this line segment that's 2. And this is, what is, oh, nope, too far, too far. This is like 3/2, right? Like up a full 1 and another half, so 1.5, so 3/2. So the slope is up 3/2 over 2, so 3/4. And also I can use the 0.45. So this, let's see, this is going to be y equals 5 plus 3/4 x minus 4. So 5 plus 3/4 x minus 4. 5 plus 3/4 x minus 4. And where's that valid? That's valid between 2 and 4. We already used 2, so I'm not going to use it twice there. We already did the work for this, so what I'm going to do is I'm going to look back at the calculator. If you didn't do the calculator stuff, go back and do the calculator stuff, rewind the video. I'm just going to steal the answer that I got here because I don't want to do it again. So let me just write this down. So I'm looking at my calculator screen. Negative x cubed over 6 plus 3x squared minus 113 x over 6 and then plus 43. So that's weird. I wonder where I came up with that. I feel like it was probably just a mistake, like, you know, and it's stuck. And that's from there to there. Okay, that's it. So not really a calculus question, to be honest, more like an algebra 2 type of question, but a good question nonetheless. You have to do this kind of thing sometimes. Find the equation of the line tangent to f of x at x equals 5. So f of 5, mostly I just don't want to find that derivative. It doesn't look like it'd be very nice. F of 5 is 3. So that's good. Let's write that down. F of 5 equals 3. All right, we need f prime of 5, which I honestly feel like I'm going to end up using a calculator on, but let's start off. So I can power rule my way through this. It's going to give me a quadratic. F prime of x is, so I'm finding the derivative of this right now. Oh, that's interesting. If I don't let go, it doesn't like duplicate itself. But as soon as I let go, it like gets a little darker if I try to do it again. That's good to know. All right, so it's negative 1/6 x cubed will be negative 3/6, so negative 1/2 x squared. The derivative of 3x squared is 6x, and then minus 113 over 6. So that's going to be really annoying to deal with. So f prime of 5 is negative 25 halves plus 30, which is like 60 halves, minus 113 over 6. I don't want to do this. I'm going to use a calculator really quickly. So, you know, you also could be using a calculator on this. Let me see. This such that x is 5. I get negative 4/3. Holy cow. Okay, so this simplifies to negative 4/3. Did not see that coming. All right, so then the equation of the line tangent is going to be y minus 3. So this is the tangent line. Is going to be y minus 3 equals negative 4/3 x minus 5. All right, can we like add that to the graph? I don't know. Negative 4/3. So if you go down 4, 1, 2, 3, 4, and then over 3. Oh my gosh, does the tangent line actually intersect the curve again? That's crazy. And then here, you know, whatever happens, happens. I think that's our tangent line. I should have done that in a different color. Let's do that in like red. So it may intersect it again. I'm going to check that on the calculator like right now. So that, I think we're done, right? So I think we've got everything. But I'm really interested to see, like, does the tangent line intersect the, because this is an interesting fact. So tangent lines at the point of tangency have the same value as the function, have the same slope. That is the definition. It doesn't say that you can't intersect the curve again. So I'm going to call it g of x, let's say. So g of x is going to be 5 minus 4/3 x minus, what am I doing? 3 minus 4/3 x minus 5. Is that right? Yes. Okay. 3 minus 4 thirds, quantity x minus 5. F of x. Did we store f of x or did we just like mess around with it? So this is f of x. So f of x is that. All right, let's see if we can solve f of x equals g of x for x. So I'm expecting I'm expecting 5 to be an answer. I also think 8 is going to be an answer. It is. What the heck? That's cool. All right, so in this problem, there's like this little extra gem where it turns out that the tangent line, for whatever reason, intersects the curve. So before, actually, I was about to like leave the calculator screen. Can I even do that? I don't know what's happening. I don't even know what I'm sharing with you right now. Okay, so that's wrong. Hold on. Going back to the calculator. Everybody relax. Okay, so now the question is, when they intersect again, is the slope the same? Well, we know the slope of the line. This is a little, if you're on the computer, you can just type derivative, and then you have to say like comma x for like what derivative. We know the slope of the line is negative 4/3. Derivative f of x with respect to x at x equals 8, not negative 4/3. So the line is tangent to the curve because at x equals 5, they have the same y value, they have the same slope. By definition, tangent line. The line coincidentally hits the curve again. When it hits the curve again, it's not tangent to it at that point, and that's not a problem. It only has to have that property at the point of tangency. So this is actually a really good problem to kind of like think your way through. Let's go back to the notes. And just, I don't really know why. I mean, you have them in front of you if you've been taking them down. But anyway, this is what we did. A lot of work. All right, so I'm gonna end this here, and I will be back in another video to just do more of this. So hope you are following along. If you have questions, make sure you're asking them of me, of someone, who knows. But I will see you in the next video. So yeah.